Open up the chat box and you can get some things.
Maybe, in case someone has some questions. Audio is good for online. Thank you.
Actually, you know what? I am just going to close it because it shows on there.
Okay.
Keep an eye on that.
Yeah.
Yeah, I
We'll
don't mind
give you
open.
the questions if they pop up.
Yeah, and then someone, maybe one of you could ask the questions in the chat.
Yeah.
Yeah, that'd be helpful.
All right, I'm going to go close the doors because it's probably going to get loud outside.
It's the presidential jet.
I have a section at the end for questions.
Okay.
But if there's something seems pressing, like, wait, what does that mean? Totally interrupt me.
Great. Well, it's noon, so we can get started. Hi, everybody. My name is Jonathan Bean. I am the director of the Institute for Energy Solutions and an associate professor in the Architecture and Sustainable Built Environment programs. Our guest today is Spencer Dutton, who works in the Sustainable Energy Department at Lawrence Berkeley National Laboratories. As a researcher, he's interested in low energy cooling, including natural ventilation in buildings, the relationship between ventilation and human health, and novel heating, ventilation, air conditioning, and control strategies. One of the reasons that I've invited him here today, which becomes clear, I think, the overall larger energy conversation, is that here in the state of Arizona, 25% of all of the electrical power that we generate is used for building cooling. So it's a lot of power, electrical power, and other energy is used for space conditioning, as you can imagine, of heating or cooling different states. But because we're in such a hot climate in places, there's so many people here, it really is a big chunk of our energy use. And we need some different ways of thinking about how to solve that problem and how to reduce the amount of energy and carbon emissions associated with it. Spencer's PhD is from the University of Nottingham in the United Kingdom. I want to leave plenty of time for him to present. He's going to take you through the start from the big picture of where we are with our power grid today, and then take you down to an actual thing that built and prototyped that aims to address some of these bigger issues. I know he'll do a really nice job of connecting the dots. If you have questions during the presentation, like understanding that sort of a structure, you might decide to hold your question until the end, or if there's something that you really need to have cleared up before we move forward, feel free to raise your hand and ask, and then we'll see it to your discretion to decide to answer or to move on ahead.
Yeah.
So great, thanks so much.
That's perfect. Thank you, Jonathan.
Sure.
Oh, it's really strange having the mic on, hearing the echo. Thank you all for coming. This is great. I know I had some stiff competition from ex-President Obama. I would probably add to what Jonathan was saying, that I've been at the Lawrence Berkeley Lab now for about 15 years. And the last maybe 6 or 7 years of that has been focused on integration of energy storage with HVAC systems in buildings, how to integrate those technologies, how to control those technologies, and how to apply those technologies in various different use cases. Okay, so the agenda for the outline of today's presentation, I'm going to talk to you guys about give you some background information about the US grid, how renewables are involved in that equation, and how that impacts the duck curve, sort of background information. I'm going to introduce the concept of load shifting in buildings and how that can be helpful. Why we'd want to use thermal storage, the applications of thermal storage and the advantages of it over, say, some other forms of energy storage. And then I want to talk to you a little bit about how we can take HVAC, heating, ventilation, and air conditioning, couple that with some thermal energy storage, particularly phase change material-based thermal storage, which is an area that I've been focused on. That's the PCM storage. Now I'll describe exactly what that is in the presentation. And then I'm going to walk you through the development of a prototype system that incorporates these technologies into something that we can actually deploy in a building and have deployed in a building. And we'll be getting some data from that very recently, or very soon. Okay, and then finally we'll have some time for some questions. All right, so background on the grid. Okay, so some numbers for context. Like currently, right now, the U.S. grid has about a capacity of about 1.2 terawatts of capacity. That's obviously growing, ongoing, moving forward. And what this plot on the right here shows, this sort of bar chart, it shows last year's or this year's increase in capacity in that grid. And if you look on the right-hand side of that plot, it's cumulative, right? So it's sort of adding up all this new capacity is being added to the 1.2 terawatts of capacity. What you can see is that almost all of that is either wind, new solar, or battery storage. Okay, so that's some important context. The overall grid right now is mostly fossil fuels. It's sort of, well, it's natural gas, a significant amount of renewables already, coal, and then nuclear. But if you add up the natural gas and coal, there's still a lot of way to go there in terms of sort of like reducing those fossil fuel consumption. The impact that this potentially has, this sort of increase in of the proportion of our grid being from renewables has the potential to create what you've all probably heard of, which is this duck curve, right? So this is the duck curve for California. So this is the California CAISO. They log all the data on electricity use and emissions. What the duck curve shows is it shows the gap between the energy demand by consumers and renewable production during the day of I don't know if it's a typical day or it's averaged over a period, but this is a representative day, right? So what you can see is over the past now nearly 10 years, like this belly of the duck, that part in the middle, is going down and down and down and down. So you're actually there are parts during the day when you've really maxed out the amount of like renewable energy that you can really add to the grid, because if you put any more, you'd be essentially curtailing that electricity use and you'd be wasting it essentially. And then there are periods that immediately after, when you've got that large period of solar energy, sun's going down, people are coming home, they're turning on the kettle, they're watching, television, whatever they do, and they're increasing their energy consumption. And that's where you get this neck of the duck curve that goes up and spikes quickly. And that's a real problem for the grid. It adds a lot of instability to the grid. And what it means is that energy providers need to have excess capacity. It means they need to have peaker plants, excess natural gas plants that they can turn on a dime, and they can quickly ramp up the production to account for all that sort of like solar that is no longer happening because it's 4, 5, 6 o'clock in the evening, right? This is a problem, right? For both reasons. One, there's a potential to having to be wasting energy in the middle of the day, and two, because you have to have all this expensive capacity anyway, right, to make up for this like increasing demand. So what's the solution to that? Okay. This has a significant impact on the potential on the actual emissions as well on that grid. So if you look at this plot, this sort of shows, and it's blocked, so it's a little bit easier to see. But you can see that as you are increasing the proportion of renewables on the grid, you can end up with significant reductions in the emissions associated with that grid. Right? So each kilowatt hour of energy that you use, depending on when you use it, depending on what time of year you use it, or depending on what month you use it, has a very different like emission profile, right? And so that's a really important consideration. And what it shows is that even in the hottest months, like July, June, August, like you're getting significant like peak energy, peak greenhouse gas emissions associated with each kilowatt hour of electricity, because you're having to compensate for that lost renewables, increase in generation, and shifting over to dirty power generation to often to meet cooling needs. Okay, so how do we deal with this situation? Like typically we try to influence the behavior of customers, the customers being residential buildings, commercial buildings. And the way that historically we've been doing that is with changing the price, having time of use pricing. So this is a representative time of use price. We've got a little increase at the beginning of the day when we might want to sort of prevent people from or disincentivize people from using too much electricity in the morning when we don't have much solar, and maybe there's a lower price during the day when we want to sort of encourage that use. And then at the end of the day, that's when we want to try and discourage people from using that energy so that we can address this issue of the duck curve, right? So this is a representative of electricity price. It's not taken from any particular tariff. But unfortunately, what ends up happening is that, without any kind of way to modify the energy use, this is the profile of energy use that an occupant of a home might use. So they wake up in the morning, maybe they take a shower with their electric shower, maybe they make some breakfast, the increase in energy, maybe they go to work and they're not using so much energy. They come back in the evening and they turn on the TV, they make their dinner, they take showers, and then they end up increasing the energy again. So it's sort of like it's against what we'd really want them to be able to do. And so what we really need to do is to introduce some energy storage. And so the energy storage allows us to potentially increase our energy use during that time of the day when it's cheaper, decrease our energy use when it's more expensive, thereby shifting our energy use in such a way that it decreases our overall cost of energy. So that's the ideal. This is the sort of how we would like to do it. But again, how do we do that? Energy storage, but what sort of energy storage? So I want to give you some sort of a framework of understanding, why can't we just all have energy storage? Why can't we just all have Tesla batteries? Why don't we just have a whole bunch of batteries and then we'll shift all that energy use and then everything will be fine. We'll be using all renewables and we'll be able to using that during the middle of the day. Well, here are some numbers. So remember right at the beginning, I talked about the grid capacity. The grid capacity of the US was around 1.2 terawatts. Let's say hypothetically we wanted to shift sorry, that 1.2 or 1 terawatt of electricity for 24 hours to account for the fact that we had some wind generation or some solar, and then we wanted to use it the next day, for argument's sake. That's 24 terawatt hours of energy storage, which conceptually it's hard to get your mind around, but let's think about what this actually would mean. There are about 3.5 million EVs currently in the US. They generally have battery sizes of around 40 kilowatt hours each. So 3.5 million times 40 kilowatt hours is about 0.14 terawatt hours of electrical storage capacity. So that's 170th of what we'd actually need to shift the thing. So you'd have to have 170 times as many batteries, not in cars, but in homes and buildings and commercial spaces on the grid in order to achieve that. It's a lot of storage capacity, and there just isn't that many batteries, that we don't have that capacity, and there won't be that capacity for some time. Okay, so what can we do? The plot below tries to show how you can have a combination of electrochemical energy storage or any forms of energy storage that provide for you electricity. It doesn't have to be electrochemical batteries. It could be, in England, they do a lot of pumped storage. So they use hydropower, they pump water up into a higher level, and then they run it through a generation, a turbine. In the scenario below, you can see you've got significantly less battery use, and then you can have those providing electricity to potentially smaller heat pumps, and I'll explain why in a second, or smaller capacity heat pumps or fewer heat pumps, and then have that actually funneling that thermal energy into thermal energy storage, which would then store that thermal energy over a period of time, and then you can access that thermal energy as and when you need it. Okay, it's really important because most of the loads in our buildings are in fact thermal. Why would you want to do that over electrochemical? It's potentially a lot cheaper. There's different pathways, like industrial pathways. You don't have to have lithium mines if you have thermal energy storage. You can use, in some cases, water. You can use ice. You can use salt hydrates. You can use organic materials. So there's a whole, you can use thermal storage in the form of just sensible energy storage in mass, right? So there's a lot more options that we can attack. The problem, as I see it, is that in order to decarbonize our building energy use, it requires the electrification of buildings and the increased use of renewables. But these intermittent renewables need more storage. Storage can come in many forms, but these electrochemical batteries can be part of the solution, but not the primary solution, because there's just not enough capacity to make batteries. Contextually, buildings use about 40% of the US energy, of which most of that is thermal. And then the space cooling loads contribute to summer peak electricity, which requires, costly activation of gas peaker plants, as I mentioned before, even if you run out, brownouts, which we saw in California, which we don't want to see. As we move to more heat pumps, as we move to the electrification of heating, which is absolutely critical in order to decarbonize our buildings, we're going to see winter peaks. And if you just do a back of the envelope calculation and you take how much gas and oil is burnt in homes for heating, and then try to imagine that being on the electricity grid, it's many times more than the capacity that we currently have. It just doesn't add up. You can't do it, right? So in order to electrify all that heating, it would exceed the current grid capacity. So how do we do that? Solutions for larger buildings like campuses, it does exist, right? There are solutions that allow for energy storage, significant load shifting in buildings, chilled water storage, ice storage. These solutions are out there, but it's not really very cost effective for like small building applications, homes, modular buildings, schools. It's just not cost effective. What we need is more integrated packaged systems that incorporate these technologies that can be mass manufactured solutions to achieve scale. And those products right now just don't really exist. So this is supposed to be my joke slide. So the current status quo of the situation is that in order to, we can leverage thermal energy storage to increase our renewable utilization. And that energy might otherwise be curtailed. Because, in some locations, we're currently, even now, we're seeing curtailed energy use, curtailed wind. We're seeing negative energy prices. So this is a plot from, this is an actual prices for a location in Millnocket, where a colleague of mine from GridWorks has been working on a project. And they're looking to sort of try to enable sort of benefiting from these negative electricity prices by sort of using energy during those periods, particularly in the low cost periods, to store thermal energy. So effectively, you can get your electricity for nothing and your heat for free, which is a quote from here. It doesn't matter. The solution that we need is building integrated HVAC systems with thermal energy storage that then could potentially achieve these HVAC energy, heat load, cost savings, whilst improving our grid reliability and supporting our renewable electricity generation. Did my microphone go off? Yeah. Oh, today. Yep, sorry. Dead batteries. That made it. All right, okay. So whilst improving our grid reliability and supporting renewable electricity through load shifting. So what did we do? 5-6 years ago now, we started a project to try and investigate this. What are the technologies that we can pull together to try and achieve this? So we started a project to investigate the integration of potentially some electrical energy storage, some phase change material-based thermal energy storage. I'll tell you more about that later. Efficiency measures to lower those building loads to start off with. So the system that you're implementing don't have to be so big or expensive or like cumbersome. And oh, is it just for this audience?
Well, online as well.
Online. Okay. Sorry about that. Okay. Combining all these technologies, including efficient air to water heat pumps, into packaged systems that we could demonstrate in real applications. So we developed and demonstrated packaging systems, both physical and in simulation. And more importantly, or potentially more importantly and more impactfully, we developed the foundational tools that we need to model and simulate these technologies, right? Because we can do an example that I can apply in my home or in a school, and then you know, without the appropriate tools, like an engineer or a consultant who's might be specifying a system halfway around the world is not going to be able to sort of like size them appropriately or make sort of decisions or evaluate the potential impacts. Okay, and so in this project we also try to work with industry partners to provide a pathway to future commercialization. Okay, so this is what I was talking about earlier, these phase change material-based thermal energy storage systems. So as you might know, when you heat a material, a solid material, or even a liquid material, right, you can be able to store thermal energy in it, and how much energy you can store in it is based on the specific heat capacity of that material. If you actually transition a material from one phase to another phase, from either gas to liquid or from liquid to solid, in that transition phase, it requires or releases a significantly more energy in that transition than you would see from just the sensible increase in temperature. So just the thermal increase in temperature. So heating water from, say, 50 Fahrenheit to 140 Fahrenheit has a certain amount of energy storage, or requires a certain amount of energy and can provide you with a certain amount of energy, but that's in fact less than the same volume of a phase change material that melts at, say, for argument's sake, 130 degrees Fahrenheit. From like, as you transition that material from 120 Fahrenheit to 135 degrees Fahrenheit, because you're transitioning in that material from solid to liquid, and it requires a lot of energy to break those bonds. So this phase change material-based thermal battery, these are commercially available products. You can buy these. They have been available in the UK for nearly over a decade now. This company is based in Scotland, and they're called Sunamp. And they're one of a few different companies that are making phase change material-based thermal batteries. Inside, it's really just a box that's super well insulated with some vacuum insulation, vacuum panels. I could explain more about that another time if you want. And then inside a sort of plastic container, there's phase change material, and within that phase change material are two parallel plate coil heat exchangers. So you can melt the phase change material by putting a fluid in that's, say, hot, for example, that melts the phase change material. And then if you want to take that heat out, you can put a cooler fluid into the phase change material through that heat exchanger, and it comes out hot. Okay, conceptually. These are great. They're great because you can have very high energy density. You can store about 4 times as much thermal energy as you can in hot water. They're completely non-toxic. It's actually food grade material, so the salt hydrate. So if it were to bust or break and go into the fluid, into the liquid, and that was part of your water heating system, it would not be harmful to you. It probably wouldn't taste good, but it won't kill you. They're non-flammable, and unlike electrochemical batteries, you can charge and discharge them over 60,000 times without any kind of degradation in performance, because you're just melting something. They're potentially lower cost than lithium batteries. Right now, they're cost comparable because of the scale. You know, we have these gigafactories that produce batteries at incredibly low cost compared to what they used to be. But currently, right now, even with a small scale manufacturing, the costs are comparable to electrochemical. So what we did is we took these concepts, these components, and we tried to create some potential systems. We imagined what systems we might be able to produce and how we might apply them to a series of case studies. Big box retail stores, small medium offices, multifamily residential. We sort of did a series of design ideas. We talked to people from Target and Walmart about whether this would be of interest to them, and we talked to schools to see whether how this would work and how they would use these systems, and multifamily too. And so what this led to was, first of all, a series of models, but then a couple of prototypes. So I'm going to talk first of all about the models that we explored and how we use those models, and then I'll talk about the prototype in a second. Okay, so primarily for this project, we're going to focus on this sort of middle one, this middle building, okay? A key part of our design process in this is using these models that I mentioned, right? Because if you don't know how, if you don't have the models, it's really, really hard to size the individual components, couple these things together, run them and control them in such a way that you can be sure that you're going to meet your building loads. So we developed this process, which we're calling model-based design process, where we create component models, verify those component models with physical testing of the components, use those components to create system architectures, sticking them together, plugging them in, plumbing them like in simulation, then performing realistic simulation of those systems within the context of a building, within the context of an environment, within the context of a tariff structure that is like realistic, and to see how those systems operate, like how they're shifting load. Are we shifting enough load? Are we using the heat pump like at times when we're not supposed to be using it? Are we running out of thermal capacity? Are we able to deliver the thermal capacity at peak that we need to? These are the sort of questions that we can all do in simulation first. And we do that all in Modelica. Modelica is a modeling language. It's just a language like C++, right? And in addition to that language, there's the tools that you use to write it in. We happen to use Dymola, but there are open source tools that you can use to work with Modelica. And then there are libraries. And out there, Lawrence Berkeley National Lab publishes a library called the Modelica Buildings Library. Inside that has a whole bunch of components related to buildings. It has rooms, zones, it has pumps, it has HVAC systems, it has all the things you might want to build if you were to demonstrate a HVAC system in a building together, or power system in a building. This is really, really super valuable because it allows us to explore it in different climates, and it allows us to test controls within that simulated environment. And then we actually put them in the lab in the field. We like have a much better chance that these things are actually going to work properly as we expected. Okay, so this is a little bit more details about that. So the tools that we're using right now are visual. They're not terribly challenging unless you kind of really go into like developing the individual component models. You can drag and drop components. Here's an example of us like dragging a pump into the space and then connecting it to a heat pump, that just performs vapor compression cycle. And then we've got phase change material-based thermal battery, and then a fan core unit and a zone. So you can bring these components in. So once you've like created your component and you've defined the interfaces to the component, made a cute little graphic, and you've defined all the equations within that object, you can use it like again in different designs, in different iterations, and create essentially a tree or a hierarchy of different sort of systems. And then you can like develop and improve your controls iteratively, running the simulations and seeing how they perform. So this is some examples of some of the simulation results that we had just in one of these buildings. And you can see this is representative of sort of like an off-peak period, right, where we're charging up the cold PCM, and consequently you have a significant amount of increased energy use from the hybrid HVAC system compared to the baseline, which has 0 during this period. And then ordinarily the baseline system would have this huge peak in the middle of the day where it's trying to provide cooling, but we're able to essentially use some of this cold storage and then utilize that during this day to shift energy. So these are all in simulation, and that's really great. But what's really important is if you can actually apply these into the real world. So that's what we're trying to do. And the next step of this presentation is on the development and testing of a small commercial building prototype. Okay, so in this particular project, this is the team that we're working with right now in this development. So it's me as the PI, and then we have Marco Bertoni from the lab as the co-PI, and we've got some support from some other people at the lab, including Armando Casillas. This effort is currently in partnership with Stanford University, of which Dan Sambor is actually the technical lead, and then Mark Jacobson is the PI for that project. This is a little bit of background information as to why we chose this sort of specific target area. And I want to go back to that prior project we talked about. During that project, we did something called the ICORPS training, which is DOE's commercialization training for researchers. So if you're at any of the national labs, or I think there are some other ways to get into it, but you can apply to join the ICORPS, or sort of join in a group with some people from a lab. And it's a way to sort of help train researchers to think more about the commercialization of the technologies and the pathways to commercialization. For obvious reasons, the DOE does not want you spending money on researching things that don't have viable application or impact. So in 2019, we did the ICOPS training. We did a lot of market analysis, and we identified some market opportunities in this space. And one of them was this space for like small systems that are currently really, really, really challenging to decarbonize. They also have the advantage of being small, and so like it's easier to manage and deal with, and we could practically create a prototype for it rather than a giant system, which would be too expensive. So it seemed like a really good place to start with it as a minimal viable product. What we wanted to do is create a drop-in replacement for something like this vertical package unit. I mean, there are systems that currently have energy storage that are small like this, that will serve small to medium buildings, like this unit this is a Stethis unit. These are great, but they also like use electric resistance for the thermal energy storage. They use bricks that heat up sensibly, very, very hot. So they have some potential heat losses there, significant heat losses. They do come with a heat pump, and that can meet sort of the baseline heating loads. But then if they ever need to call from that storage, it's storage that was heated from electric resistance. Electric resistance heat, not as efficient as a heat pump. So I'm trying to have a system where all of the thermal energy is coming from a heat pump. All of that energy is going to be getting, we're going to be getting COPs, coefficients of performance of higher than, ideally higher than 3, right? So 3, you put in 1 unit of electricity and you get 3 units of heat out. That's ideal. And another reason why this was really valuable and important to us was that we got a lot of feedback in this market analysis that showed there was interest with facilities managers and school districts. And they were really struggling with a pathway to decarbonize all this sort of like these small systems that they have on school buildings. They don't have necessarily the electrical infrastructure to have electric resistance heat, so they can't do that. They don't want a giant heat pump, because then the capacity of that heat pump would require, again, upgrades to the electricity. They wanted to have a system that was electrified, decarbonized, but also didn't strain their capacity. And they were also super interested in this concept of shifting system, like upfront system costs into operational costs by using something called conditioning of a service. And I can tell you more about that another time if you like. So this is the concept that we've been working on for this prototype. If it's successful, we would be able to, validate this prototype of a new type of equipment that can be, cost effectively decarbonize these hard to tackle buildings. It'll enable electrification in these capacity constrained locations. It will improve the resilience of the building, because you can store a whole bunch of cool for a whole bunch of heat, and then as long as you have a small amount of electrochemical battery, if the main power is cut off, you can still provide a minimum amount of cooling, a minimum amount of heating in those situations to keep people from getting ill or dying even. And it addresses a huge market. I mean, these small to medium commercial buildings that are like really underserved by these these sorts of technologies. It represents about 94% of all commercial buildings in the US are small or medium. Okay, in fairness, that's only about 48% of the floor area of those commercial buildings, but that's still a huge amount of floor area. Once we've developed this concept, turn it into a prototype, that's not to say that's the end game. Like, we can apply the same concept to various different applications. As we've done in models, we could build a system that was like related to a multifamily, as we are, or for a big box system. Hold on one second. So our approach has been combine commercially available components, put them together based on the results from simulation, test those first in a lab, try that system in the field, optimize the controls based on the feedback we get from its operation on site, quantify its performance, its load shifting, its energy costs, its greenhouse gas reduction potential, and then work with industry partners to develop a more integrated system. So buy stuff, put it together, make sure it works well, then say, look, this is how, if you took these component technology concepts and then made them into an integrated system that had all of the components packaged together so it can be mass manufactured, you've got like all of the controls inside that unit. So you're not having to have third-party controls. You're not having to bother Johnson Controls or some other controls company to like come in and like develop controls for your system. And it can be relatively easy to install, drop-in replacement for existing system. And the power itself, the thermal energy storage itself, could be potentially modular. So you've got, in a climate like this, you might want to focus on cold storage. In a climate like Berkeley, you might want to concentrate mostly on heating storage, maybe a tiny bit of cold storage. So it's a flexible concept. So what we did is, as I said, we started with these models, then improved the models with by characterizing the performance of the physical systems in the lab, and then built these up into a prototype system. And this is sort of like us putting the components together in a system. So what we see here is like the shell of the prototype with, you can't really see, it's hard to see, but there's two thermal batteries inside the system. There's like one at the front and one at the back, and one stores cold thermal energy, one stores hot thermal energy. So one has a melt point of 11 degrees C, which is, you know, I can't do that math in my head just now. And one of them is 50 degrees C. So one hot, one cold. Conceptually, this is how it works, right? It's pretty simple. It's not that simple, but it's simple. We've got an air to water heat pump, provides hot water, in this case for the heating charge mode. It travels through the system, goes into a hot phase change material-based thermal storage, loses heat, so the color changes to orange, comes back to the heat pump, goes in a circle, melts this phase change material. That would be the charging mode of operation, so that you get to. Similarly, in the cooling, that's what would happen. You'd charge the cold thermal storage with this, with very cold water of around 5C or 6C, and then it would be leaving around 11 or around 11 or 12C, depending on how charged the battery is or how discharged it is. And then if you wanted to use those batteries, you'd do something like this, right? So we'd use a different pump right now. So there's a pump in the air to water heat pump, and then I use a separate circulator pump that pumps the fluid round in a circle through the air handler, back round, through the battery, heats up, comes back round, goes through here, around here, and it's the air handling unit. So, and then gets cooled down again. So it's, I tried to keep this consistent with how it's structured in the box. So this represents the valve that's on the left, and this represents the valve on the right. Just so this could have been greatly simplified, but it makes sense if you're actually looking at the physical system. So that's utilization of the hot storage. And then conversely, if you wanted to use the cold storage, you can imagine from the air handler, you've got relatively warm fluid coming back from it that then gets cooled down by this cold storage and comes back and gets sent back to the air handler in a loop. And during these like use modes of operation, you're really not using a huge amount of electricity, right? So it's just this pump uses about 40 watts. By contrast, this air to water heat pump can use up to 4 kilowatts. So that's a significant like drop in electricity use during that period. So progress. We've actually got this system currently now on a field site. We started a new collaboration with Stanford, as I mentioned. They have these two side-by-side buildings provided by a DoD project that they're working on. So it's ideal for comparing the performance of our system with the performance of an all-electric PTAC system. This is essentially an off-grid microgrid setup where they have various different distributed energy resources. And so their goal is to balance all these distributed energy resources, their electrochemical battery that's in the middle, can you see there, the loads that they have, the solar generation, potential for some wind generation, like balance these all, including the space loads as well, right? And then the thermal energy storage loads. And now they have this additional capacity. They have the ability to sort of look into the future and say, well, we're going to need cooling, we're going to need heating in 6 hours time, but we have a whole bunch of excess electricity. Great, let's store that in the form of heat. Let's store that in the form of cool. That's the most efficient way for us to store energy right now. Okay, so where we're at right now is we're in the process of commissioning the system. We got some initial preliminary data for it, and we're going to be doing field evaluations beginning in the fall of 2024 to summer 2025. So we'll be getting a whole winter season and a whole summer season of data. This was our first set of data. So this shows you here, if you look at this plot over on the right-hand side, the little dotted line here, this is the electrical use of the heat pump. And you can see it goes up, and then it goes down. And the two different sort of like operational periods here, the first period in like kind of light blue or baby blue is like, that's sort of representative of off-peak. Maybe it's occupied system where you're trying to cool the space in order to maintain comfort loads, but you're also trying to like store cooling for later on in the day. And as a result, if you see you've got a significant amount of electricity use from the heat pump. If you look at this red line here, this is the power of the heat pump. So this is like thermal power being delivered by the heat pump. Some of that thermal power is getting sent into the cold storage here, the yellow line. Some of that thermal power is being sent to the air handler and is being distributed into the space. And if you look, the green plus the yellow effectively makes the red with some small losses. You can see that in the plots of temperatures where we've got the green line here is the cold, is the average of 3 temperature sensors that are inside the phase change material-based thermal battery. These temperature, you can see it's like falling and falling and falling and falling, and then you get this precipitous change in temperature here. And so that's going from, I think, around 53 C down to below the freezing point of the material. So this second phase, the pink, light purple phase on the right, this essentially represents a period where you might be thinking of it as on peak. So this might be a period where you're trying to use less electricity and take advantage of the cold storage that you have. So we're in this mode of operation, we're just drawing cool from that battery and transferring it to the space. And as you can see, both the yellow and the green line are sort of very similar levels. So that's basically the energy that's coming out of the battery is going into the space. And the electricity that we're using at that point is significantly lower. It's significantly lower. It's around 50 to 100 watts, depending on what's happening within the system. So compared to 1,000 and 1,300 watts at peak, say. This compares to, so we have some heating operational data as well. You can see that the power of the heat pump is significant during this sort of period where we're trying to heat the space and store heat in thermal storage. Then if we're just trying to heat the phase change material, it's just heat the phase change material because our room is warm enough. Then this is this sort of mode of operation, and we could see that the hot phase change material is sort of like heating up and heating up and heating up past its melt point to the point where it's completely full. And then our room is comfortable and our phase change material is full. So we're standing by the system. So we've done all we can at this point. That's an example of some data. Some really powerful lessons learned from this were, this is really hard. Like getting these things to work together, getting the heat pump to operate in the way that you want it to do is really challenging and sometimes not possible because you don't have access to the internal control logic of that heat pump. So it might have logic that says, when I see the water coming back at, let's say for argument's sake, 51 degrees C, because we're trying to melt our phase change material and the melt point is, between 50 and 52, 53, it's going to see that water coming back at the high temperature and think, oh, I've done my job. It looks like I've managed to heat up the space that I'm heating, and the return water temperature is 51 C. I've done a good job. I can turn down my heat pump. And that's not what we want. What we want is to actually have the heat pump pumping out as much heat as humanly possible until that battery's full. and that isn't what happens. So there's some challenges around managing sort of like the operational needs of the system when you're trying to incorporate these components together, and the way that the heat pump was designed to operate for its regular use. Using these models, it saves a lot of time and money if you're developing a system, because it's too easy to just throw a bunch of things together and see if they work. But if you don't size the heat pump correctly, if you don't size the storage correctly, if you don't size the pump correctly, it's not going to work very well. You're going to have things like cycling of the heat pump. Cycling of the heat pump means you're operating, it's operating for a short period of time and then turning off, operating for a short period of time and turning off, and that really hits your COP. Barriers and challenges to this technology. Okay, so if applied more broadly to the market as the market currently looks, it is highly dependent on the energy tariff that you're exposed to. And if you don't have any variation in tariff, the economics of this are a hard argument to make. So you can't use cheap electricity when it exists because all the electricity costs the same. That's a different argument if you have your own solar, but that's a separate thing. Currently, right now, in the residential market space, at least in California and like in a lot of places in the US right now, residential electricity tariffs don't tend to vary significantly between on and off peak. That's changing, and it's going to be changing more, and it's going to need to change. But as things stand, it's like that can be a challenge. And yeah, this is the electricity market structures currently prevent end users from fully capturing the financial benefits. You know, that plot that I showed right at the beginning where you have those negative electricity prices. People never normally see negative electricity prices in the residential retail market. You don't have access to it. There's a new thing in the UK called Octopus that my dad has got, actually, where the company Octopus has a little box and they act as an aggregator. And so they effectively pass on those like negative electricity price savings to the customers. But that doesn't exist here right now. And if it did, then there'd be a much greater potential savings for these kinds of technologies. So this is something that's a takeaway from this. Progress towards future commercialization. A lot of these individual component technologies are undergoing innovation. They're undergoing cost compression. We're getting new heat pumps. We're getting new phase change material-based thermal batteries that are potentially lower cost. And so, transitioning from what this is as a research project and a prototype to a potential commercial product, what I have demonstrated is not necessarily what I foresee being like the ingredients for the fully commercial unit. Like, we're going to get a lot of innovation over the next few years, and we can incorporate these technologies together and make something that's relatively low in cost and has a potentially very large impact. And we wrote a series of papers on this work, and this is the bibliography. I don't expect you to write all this down, but the slides should be available. And any questions? This is an example that I wanted to show of like a potential target for this kind of technology for school buildings, where there's many of these individual systems. There's a lot of space underneath. By utilizing that space, you could just change the form factor very slightly and have a whole bunch of thermal energy storage and electrify these systems using the technology that I was just suggesting. Okay, any questions, anybody? Jonathan, is it?
I have a question, Spencer. Can you tell us a little bit more about how the lab works with different universities?
Yeah.
Sure, those kinds of collaborations are.
Yeah, so it really helps in our proposals if we have a broad range of stakeholders and parties in those proposals. So typically when we put together a proposal, we will try to get at least a couple of industry people, industry organizations involved. And if we can get a university involved at the same time, that's really helpful. In part because a lot of things we're trying to do really lend themselves to small projects for universities, and we can get students in, and they may have their own funding, and we can give them a keystone project to work on, and it's just it aligns well with our broader mandate of disseminating information and coordinating with stakeholders in universities. So generally, we'd try and get in proposals together.
So I got a simple question. Right now, if you put a unit outside, you can comment on the thermal insulation because, for example, putting Arizona outside is so hot. So if you store the cold temperature.
Yeah. So that's a really good question. Like, how would that even work? You've got something outside, you're trying to store cold outside. Let's go back to that phase change material-based thermal battery. So this unit here, this is vacuum insulation. It's like panels. So what that is essentially a coarse kind of powder, if you will, that they use. And then they use that powder, and then they compress the powder in like a pouch or a panel with a radiant barrier, and then they suck all of the air out of that panel, right? So from inside of that panel, and so what was originally a powder then becomes effectively solid because it's under such high compression, and the insulation of that, because you've sucked all the air out of it, and you just have these granules that are just touching just a little bit, and they don't insulate very well. I mean, they're quite good insulators anyway. Means that you end up with like a R50 insulation for what is about a half an inch or 3/4 of an inch panel. Like incredibly high resistance. So it's yes, in very hot climates and in a situation where you're trying to store coolant at 5 degrees C, you will see thermal losses. But what we're trying to do here is we're trying to shift typically within a few hours in a day. We'll be trying to generate coolant in the morning, say, and using it later on in the afternoon or during at 4 o'clock. Or maybe you're using some of the excess capacity in the middle of the day and shifting it by 3 or 4 hours. And so the thermal losses over those time periods are not huge. Like if you were trying to keep this for like days and days and days, yeah, totally. Yeah.
You talked about the importance of sizing and melt point calibration for like each specific implementation. And I was wondering, first of all, that sounds really labor intensive. So what do you see as the path to scaling thermal energy storage from that perspective?
Right, so you wouldn't need to do that necessarily in every single application. Like just as right now, if you were to buy these systems, these barge systems, right? It's not sized. There are not hundreds of different sizes for every different climate. There's a few different sizes, and then in the particular market that you look at, the engineer will say, oh, we typically get away with a 3-ton unit in this market, or you need a 5-ton unit, right? And so that's the thing. You do it once, you get the sizing appropriate for the heat pump in the design, you build the design. These sort of sizing and modeling and controls development tools. It's not for the specific application that you put in the building. It's to design the system itself, right? So you do that once or twice or 3 times, right, to get a good system for system design concept. Then you mass manufacture it, and then you just throw it out, right? So sell it. It's not over and over and over again. By contrast, that is kind of what you have to do if you don't have these mass manufacturable systems. If you just have systems where, like, if we were to contract a mechanical engineer to provide some thermal energy storage for this building, they would come and they would like design a custom system. They would give you, design drawings, and they would like size the system according to the loads of the space, the thermal energy storage, and the space that you have. And so I'm trying to put together systems that can be more like commodities. more like you know, an RTU, and you know, a rooftop package unit. Yeah, Jonathan.
Sort of building off of that question. One of the roadblocks to more heat pump adoption, just standalone heat pump adoption in the residential market, it's really hard for installers to know with confidence, feel confident that the unit that they selected is going to be able to provide, in particular, the heat output that the customer would expect.
Right.
Especially if they're switching, say, from the gas furnace. And it's really difficult. I think a lot of contractors will say, well, why should I put in this heat pump where I'm not exactly sure if it's going to meet heat output requirement. But if I put in a gas furnace that's rated at 40,000 BTUs, I will be absolutely sure that my customer is not going to be cold. So have you thought about sort of positioning the thermal storage as a guarantee in a way of providing a baseline level of capacity and therefore kind of taking away some of that hesitancy or confusion or additional complication that right now is imposed upon installing the person selling?
Yeah, I mean, that is what it does. I mean, it does provide that additional capacity. Yeah, and I mean, I'm not in the business of selling these systems currently, so I don't have to face that challenge. But you're exactly right. I mean, this is what we're trying to. This is the point we're trying to make, is that by combining the two together, it's an enabling technology. It allows you to use these heat pumps in situations where it's either the electrical need would be too large because you'd have to have a large heat pump, which could be potentially very expensive. It allows you to put in situations where people might be, might otherwise be concerned about the capacity they're able to get out of the heat pump, because you can say, look, well, you run the heat pump all day, you charge up the thermal energy, and then when you need that capacity, you can just draw upon it. And it is challenging. It is challenging to make that argument. Like, we've had conversations with mechanical engineers and with people that specify these types of systems, trying to make that argument, and they don't want to hear it. And they don't want to hear it in part because sometimes they're very, very stuck in there, like, well, that is the design capacity that we need to provide. That's the kind of, like, we need to be able to provide that in an ongoing way indefinitely forever. But that isn't really how buildings work. You never really have that peak continuously. It's the peak is the peak, and then 3 hours later, it's no longer the peak. Okay. So yeah, to your point, it's one of the main advantages of integrating thermal storage with heat pumps. Yeah.
Thanks. Any last questions? Yes.
Sure.
You said you have something similar in England using?
No, these phase change material-based thermal batteries are available in the UK, and companies are installing them in homes right now.
In the UK.
In the UK, thousands and thousands of units. Yeah.
How's it doing over there?
How's it doing? It's doing well. Like, I think it's doing well. I mean, the company's really growing. They will often combine them with a heat pump. You can use them in a couple of ways. Some of the batteries have electric resistance elements in them, and so in the UK they had a lot of incentives for installation of solar, a few years ago, which are now less no longer as good. You don't get as much money as for providing your solar back to the grid, and so people are looking for ways to use their electricity in the home, not having to sell it cheap to the grid. And so this provides a relatively inexpensive way to do that without the need for a heat pump, because they can have electric resistance in the battery. They just use the excess solar, store it in the battery, and then they can use that to either be their hot water source or augment, like supplement their heating system. And they're really small. Like, you can fit these things, in you know, one of the challenges in the UK is like the size of the buildings and the size of the available space you have, right? So all of our heating systems fit in little cabinets. You know, like in my home in California, I have an entire room that has my heating system in, right? In England, that's not an option. It's in a closet, and that's why they have these. So that system lends itself well to that. But if you want to couple that with a heat pump, you can do that too, and people do it. I've seen that system too.
Thank you so much, Spencer, for visiting us in Arizona. It's fun.
You're welcome.
You'll be chatting again soon. Show us the next iteration of the project.
Thanks.
Thanks so much.